Okay, here we go. This is the next section that we're going to be talking about in our next class period. It is 1.4 on the basic rules of algebra. And so the basic rules of algebra are really leading us towards simplification. So I just write the word here, simplify. That's what we're heading towards. Remember, we said algebra was evaluation. We've talked about that. Now it's simplification. Now there's lots more simplification things that we're going to do over the next 2 or 3 classes. Intermediate algebra, pre-calculus, if that's the direction you're heading. There's always simplification things you have to pay attention to. But they all come back to basic algebra, most of them. And so we really want to understand those basic rules of algebra. So first of all, we're going to spend a little time on algebraic expression vocabulary, and then we're going to learn the 3 properties that help us simplify, or at least 3 of them that will help. The commutative, the associative, and the distributive properties. All right? We want to talk about those and we want to actually see how they work. Your goal here is understanding. How do they work? How am I using it either in my mind or on paper to help me? The one that you'll physically show most of the time is this one, the distributive property. The other 2, the commutative and the associative, tend to be things that we do in our head. All right? And I'll show you what I mean by that as we go forward. And then finally, we're going to end up with like terms. And once we define like terms, we can then begin to do the first situation of simplification, which is simplifying algebraic expressions. And I'm going to use like terms, and I'm going to connect it back to basic arithmetic. And I'm going to show you that you've known this all along. And big shout out to my students who don't like variables. I'm going to show you that you've been doing this sort of thing all along in basic arithmetic. It's just been hidden behind the scenes and nobody used this vocabulary to bring it out. In fact, we'll do that quite a lot in this little time. All right, let's get going. And x squared. Oops, sorry about that. I apologize. So here's a vocab we need to be super familiar with, all right? And when we have an algebraic expression. So let me write an algebraic expression up here. 4x squared minus 3x plus 10. Okay, that's an algebraic expression. So what are the terms? Terms are the objects that we are adding and subtracting together. Okay, so for instance, 4x squared is being, if you wish, added to a negative 3x, or 3x is being subtracted from 4x squared, okay? So we would say that 4x squared is a term. We would say that negative 3x is a term, or the opposite of 3x, and we would say that 10 is a term. Now, subtraction in algebraic expressions becomes negative signs when we talk about terms, okay? So we kind of think of everything being added together and we're just either adding positive terms or adding negative terms, all right? So those are the terms. It's just the individual things we add or subtract together. A coefficient. A coefficient is the number times the variable. So the coefficient of the term 4x squared is 4. The coefficient of the term negative 3x is negative 3. And the coefficient of 10 is just 10. Now, this did not have a variable part, okay? And so we give it a special name since it doesn't have a variable part. We call it a constant term, okay? A constant term. So whenever you hear people say, what's the constant, all right, or what's the constant term in lots of variable expressions and equations, the constants are always the terms without a variable, okay? Constant term. So what are the factors of the term? Well, if we look at 4x squared, then the number portion, the 4, this, well, let me say it this way. This really says 4 times x squared. And so this is a product, and remember, the two individual parts of a product are called factors. And so we have two factors here for, flip the page there. So we have two factors there, 4 and x squared, okay? Now, on the negative 3x, we also have two factors. It's negative 3 times x. So one factor is negative 3 and the other factor is x, okay? So the factors of the term are the numerical parts, the coefficients, and then the variable parts. And we looked at those as factors. So what are going to be like terms? Like terms are going to be terms that have exactly the same variable part. A term with exactly the same variable part. Now, when I say exactly the same, I'm not only talking about how the variable needs to be the same, but it is also understood that the exponents need to be the same as well. Because in reality, this x squared variable part is x times x. So there are two x's being multiplied together, whereas over here in this one, this is an x. So these are not like terms, all right? So keep that in mind for later. All right, let's go to the next page. So really the next big thing is talking about the properties of algebra. Now there are more properties than these three, but I call these the manipulating properties, okay? They manipulate things. In other words, they move them around, or they regroup them, or they tell you whether to multiply or add. So they tell us something. And these properties are the commutative property, of addition, and the commutative property of multiplication, okay? Now, how does the commutative property work? What does it do? Well, that property is written algebraically this way. A plus B equals B plus A. That's the commutative property of addition. And the commutative property of multiplication is A times B equals B times A. So what you can see here is this just changes the order that you do things in, okay? Things actually switch position, if you'd like to talk about it that way. Now, remember how magical this was in elementary school when you realized that 2 plus 6 was exactly the same thing as 6 plus 2? I remember working with my son when he was young, and he could do 6 plus 2, right? He'd say 6, and then he'd go 7, 8. And he would get 6 plus 2 is equal to 8. But boy, if I ever asked him 2 plus 6, he just did not get it. But then, all of a sudden, somewhere along the way, either a teacher taught him or he realized it himself or something, he eventually realized that these were the same thing. And it was okay for him just to look at 2 plus 6 as 6 plus 2. he could actually visualize it that way, and then he could do the math in his head. All right? And so a part of these properties is to simplify our process. Another place we use the commutative property would be, you might see something like this: 7 plus 5 plus 8 plus 5 plus 3 plus 2. All right? And you're supposed to add those all together. But what you do is you say, oh, wait a second. If I switch this 5 with this 8, then 5 plus 5 is 10, right? And if I switch the 3 with the 5 and then switch it with the 8 and switch it with the 5, then I have 7 plus 3 is 10, right? And all this switching around and so forth, where things move to a different position, what you're doing is you are commuting the things. And you can always do it with addition and multiplication. Now, here's a point I want to make. Instead of having, if you do 7 minus 5 subtraction, notice 5 minus 7 these are not the same. They are not equal. So subtraction is not commutative. In the same way, division is not commutative. Okay? They're not the same thing when we just switch the order. This only works for addition and multiplication. However, if we say subtraction is really, and I'm going to put this in a different color, it's really addition of the opposite, or multiplication or division is really multiplication by the reciprocal. If we do that, then we make this have the commutative property, because now it's an addition problem. And now it's a multiplication problem, not a division problem. All right? This is the big deal that your algebra book's not telling you about. This is why the only real operations we have are addition and multiplication, and that very often it is good practice to think of subtraction as adding the opposite and multiplication as multiplying by reciprocals. Because then this property works. And the commutative property is fairly important. If you study grad school abstract algebra, you see that not all things are commutative, but commutative makes things nice. And our number system is very nice because it has this property. Okay? And not only that, it has this property for two different operations, both multiplication and addition. All right, let's talk about the associative property and how it's different. Associative property, one of the things I want you to know, it also is for multiplication and for addition. It works for both. But one of the things I want you to notice is that everything is always in the same order. All right? But what changes is what we group together. Okay? So in other words, we're deciding to add other things first. Okay? That's the associative property. Okay? Commutative moves actual numbers. Associative doesn't move the numbers. It moves which ones we group together. Okay? That's pretty cool. All right? Now, this works for multiplication as well. A times B times C is equal to A times B times C. All right? Now let's go back to that problem I had earlier. All right? 7 plus 5 plus 8 plus 5 plus 3 plus 2. So I want to do that. Now, what I notice is that I can swap the 5 and the 8 here. So I could rewrite this as 7 plus 8 plus 5 plus 5 plus 3 plus 2. And just so you know, I have switched positions on the 8 and the 5. Okay, so I have used a commutative property right there. However, what I want to do is I still don't want to add the 8 and the 5. I much rather would add the 5 and the 5 first. So what happens then is I basically swap a grouping. There are no parentheses here. But instead of going, okay, 7 plus 8 plus 5 plus 5, I want to add 5 plus 5 first. So what I'm doing is I'm grouping the 5 plus 5. I'm regrouping, all right? Plus 3 plus 2. Essentially, these were kind of grouped before that. Those were the ones I switched. They were grouped, so I'm switching the grouping. So it's not always apparent. There aren't always parentheses there that say you're changing what you're going to add first, all right? But that's an associative property, okay? And that's really the difference. Commutative, notice they changed position. Associative, basically, they changed the grouping. You're saying, I want to do these first, right? And by order of operations, whatever's in the parentheses is what you tend to do first, okay? And so that's what we've done. Now, but we can see also that I'd like to combine the 7 and the 3. So I can sort of put, all right, if you wish, an imaginary parentheses around all of this, and I want to switch the 3 with all of these. But since they have, so I'm switching 3 with what's in the parentheses. So when I do that, I end up with 7 plus 3 plus 8 plus 5 plus 5 plus 2. That switching position, that's a commutative. I've now changed the order of the actual numbers. But instead of having the 8 and the 5 plus 5 grouped together, I really want the 3 and the 7 grouped together. And so I'm going to switch the grouping, all right? Add the 7 and the 3. Now I have this 5 and 5 I'm adding, the 7 and the 3. And now basically I want to swap the 2 with the 5 plus 5, and so it's with the 8. So in mental arithmetic, you're going like, oh, 7 plus 3, 5 plus 5, and 8 plus 2, this is equal to 30. That's what you're doing mentally. But what it involves are these properties, commutative and associative, which have numbers switch position and then change which ones I'm going to add first by determining that with parentheses. Okay? That's commutative and associative. And this is probably the main place any of us have ever used it, is when we're adding a bunch of numbers and when we start to change the orders because they're easier to do. A lot of times, I might have a 7 plus a 6 plus a 1, and I'll choose to do the 6 and the 1 first and get 7, and then add 7 and 7. And so rather than just go 7 plus 6 is 13 plus 1. I don't know why, but figuring this kind of switching and stuff out is really, really important, and an important reason we use properties. So almost always in algebra, when you're doing something in your head, you're using commutative and associative. okay, to kind of switch the order of things. All right, last property. Distributive. The distributive property involves both multiplication and addition. It's what I call, it's a connecting property. It tells us how to multiply and add when they're both in a problem. And it looks like this. If you have A times a quantity, B plus C. Now notice there are two operations here. It's not just addition. If it was just addition, it would be associative. But it's not just addition, it's not just multiplication, it's both of them. And so what do we end up with? Well, what happens, and I like to illustrate it this way, is I have to take the A and I have to multiply it by every term. Remember, terms are separated by additions or subtractions. I have to multiply the A times every term. So I end up with AB plus AC. All right? The distributive property is super important because when we go this way, it's called multiplying. But when we come back this way, it's called factoring. And so you guys probably remember you had a whole chapter on factoring. The distributive property is the key to figuring out how to find prime factors of certain algebraic expressions called polynomials. Okay? Which is something we'll do later this semester. Alrighty. So this is how it works. Quick example, negative 3 times 2x plus 5. So I'm going to take the negative 3 times 2x and the negative 3 times 5. And so sometimes what I do is I write that down. And often when the negative 3 is in the middle of the problem, I put it in parentheses to separate that negative out. But anyway, I end up with negative 3 times 2x is negative 6x. And then plus negative 3 times 5, that's negative 15. So I can put subtract 15. And that's how we do the distributive property. So we're going to use the factoring aspect of the distributive property here in a moment to show us how to collect like terms. But that's distributive. So the last thing we need to do is called collecting like terms. So if you'll remember, a like term is a part of an algebraic expression that has the same variable part, okay? Or they're both constants, all right? So for instance, I'm going to write an algebraic expression. 5x minus 3 plus 10x plus 7, okay? Now, when I look at this, what I notice is that the 5x and the 10x are like terms because they both have exactly the same variable part. I also notice that the negative 3 and the 7 are like terms because they're both constants. They both don't have a variable. So those are like terms. So the very first step on these problems is to ask yourself, what are the like terms? And if you wish, you could then use the commutative property to swap positions. So I'm going to write 5x plus 10x because those go together. And then I'm going to put minus 3 plus 7 because the constant terms together. So in other words, I've used the commutative property to switch the 10x and the negative 3, switch their positions. Now I'm going to use the associative property, and when I collect like terms, they're really saying add or subtract. That's what they mean. Add or subtract the like terms. So I can see really quite obviously negative 3 plus 7, I already know that. That's just basic arithmetic. That's a positive 4, right? Negative 3 plus 7, or if I wish, 7 minus 3, that's plus 4. So now the 5x plus 10x. We have done this before, and I'll tell you where in just a moment. But think of it like this. I got 5x's, and I got a pile of 10x's. So if I add those two piles together, how many x's do I have? And what we see is we just add or subtract the coefficients. So that is 15x. And we have now collected like terms. If you have an algebraic expression and all like terms are collected, then your algebraic expression can be said to be simplified. All right? So this is our first simplifying technique, collecting like terms. All right? Now, why is this 15x? Well, it turns out it's our old friend, the distributive property. If you look at this, 5x plus 10x, both of these have a factor of x. So we're going to undo the distributive property. We're going to pull the x's out, factor it. So we're going to put x times 5 plus 10. All right? And that is x times 15. And by the commutative property, I can write that as 15x. It's the distributive property which says you can add things together that are like terms. And that's why they have to exactly match. That's why you can't add an x squared and an x together and combine them, because they're not exactly the same. All right? And it's because you can't factor it. Now, we're going to come back and do a lot more factoring, but in this case, it's just undoing kind of the arrows that I drew with the distributive property, and I pull the x out, what I multiplied by the 5 and the 10, and then I add it together. So that's why it works. Now, most of us do this kind of work in our head, but this is why it works. So I did say I want to show you one more thing about like terms, that you've been doing this all your life. So for instance, let's take 367 and add that to 422. All right? Now, you and I line numbers up like this because they have the same place value. All right? And when we add, we take 7 plus 2, 6 plus 2, and 3 plus 4, and we get the answer 789, and that would be correct. But what really is place value? Place value is just the variable in this problem, in a sense. It acts like a variable. If I take the 367 and I write it as 3 times 100 plus 6 times 10 plus 7, this is called expanded notation, and you might remember doing something like this in elementary school. And then I'm going to add that to 4 times 100 plus 2 times 10 plus 2. And so what you can see now is that this 6 times 10 or 2 times 10, that's like writing 6y and 2y, where the y is the 10. And so because they have the same place value, they are like terms, and that's why we add the 6 and the 2 together right here. Not because they are lined up, but because they have the same place value. And that's why we line them up. And the lineup just helps us add the correct ones together visually. Okay? Just imagine if our symbol was for 10 was like a variable, like y, and we understood y as a symbol to be the number 10, right? Then 100 would be y squared, 10 times 10. So these are both the y squared terms. So we have 3y squared plus 4y squared. So by distributive property, we can add their coefficients. So the secret to all addition and subtraction that you did in elementary school is place value, which tells us which terms are like terms, and it's the distributive property behind the scenes that allows us to add the correct things together. Okay? And so that's why the distributive property is so important. We've been doing it all our life. It's just never probably really been called that or focused on in this way. But once you get to algebra, everything we do in algebra, we've almost done all of it before. And all the variables could very easily be thought of as the base or the place value of the number in a lot of cases, and that could help you understand how to do the problem if you can see that. All right? So that's all I have for you from this section. Hopefully you enjoyed these 2 videos. What we're going to do tomorrow now is I'm going to start giving you some problems in class. You can work on them. We'll probably work on them individually tomorrow, and maybe we'll go to teams or something like that where you can work with a partner. But the goal will be to help you have a good feeling for how to do the homework. And then the next day, before the next class, you'll do the homework, and then there will be another set of videos. All right? Okay, see you later. Good luck. Bye.